So that will be 3.3 meter multiplied by 1.8 meter. Now we need to calculate the NC based on the length over diameter ratio. We're gonna have here two ratios, and it's safer to be on the conservative approach to take the lesser value we obtained here from the two dimensions, and we're gonna take this value because that will give us lower NC value, and consequently we're gonna have lower bearing capacity value, okay, because we're gonna have smaller NC value, okay, according to this chart. As the ratio of length over diameter ratio decrease, the value of NC decrease as well, and that will be the worst scenario or the safest scenario to consider here. And that will give us, considering this value 2.27, using it here, 2.27, somewhere here, that will give us approximately NC value is equivalent to 8.5. Okay, if we substitute all these values here, NC equivalent to 8.5, CU value 75, and the rest of the values here, we're gonna get PU value according to the block approach 6.1 meganewton. Obviously, we need to take the smallest value here as the bearing capacity of the Polygroup, which is 1.56. Therefore, the load carrying capacity of the Polygroup alone is 1.56 meganewtons. So after we find what's the load carrying capacity of the Polygroup, which is 1.56 meganewton, we need to find what's the settlement of this pile systems, because to find what's the settlement of the Polygroup system with the raft, we need to separate the Polygroup from the raft and to find the settlement of each system separately from the other one. So to proceed with the calculation for the settlement analysis of the Polygroup, this is the layout of the Polygroup, which is 2.5 meter by 5 meter. This is the pile cap. So we need to find what's the effective cap area for each pile. This is the effective cap diameter of each pile. So to find out that, this is the formula of the circle, okay, the pile cap itself, okay, to find the DC value, and that's multiplied by the number of the pile, and this is the cross-sectional area of the raft area here, because everything should be contained within the raft itself, within the raft cross-sections. By applying this formula, we find that the effective cap area or the effective diameter of the cap area is 1.629 meter. And then we need to find what's the DC over D ratio. DC is the effective cap area divided by the actual pile diameter, or the diameter of the cap area of the effective cap area divided by the diameter of the pile. That will give us 5.4. Along with these value, we can find what's the value of RC value. Okay, using the chart you have already learned in your lecture notes. We can see that the value of RC is 0.9. We need to find what's the settlement of the cap unit, because what we have been given here, we have been given what's the settlement of the standalone pile. This is using the load test, gave 15 millimeter divided by 500 kilonewton. So we need to divide these two numbers on each other. 15 millimeter divided by 500 kilonewton. That will give us what's the settlement of the standalone pile. It will give us this value here, but we need this value, which is the upper value, settlement of the cap unit, and that's how we calculate it. We got what's the value because we got the value of RC from these values here. RC is equivalent to 0.9. So obviously the value of the settlements of the cap unit is equivalent to 0.027 millimeter per kilo in Newton. And then to find what's the settlement of the Polygroup itself, we need to separate the piles, the one on the side from the one on the center. So we're gonna call the one on the side as A, we're gonna give them the symbol A, and the one on the center, we're gonna give them the symbol B. Because it's a flexible raft, we know that the settlement at the center will be more than the settlement at the corner. So we need to find what's the settlement of the of the side piles, and we need to know what's the settlement of the center piles, of the pile on the center. And we know that that the settlement of pile number 1 will be due to its own settlements, and the settlements of the adjacent piles. So the settlement of pile number 1 will be due to its own settlements, and it will be also affected by the settlement of the adjacent piles 2, 3, 4, 5, 7. And that's why we need to create this kind of table to find out what's the settlement of pile number 1, okay, which is, as we said, due to its own load, and due to the loading, and due to the interference from the adjacent piles. So we need to create a table like this one's. This is the spacings. So first we need to take one of the side piles, okay, and to create these tables. And we need to find what's the spacings between this pile and the adjacent piles. So for instance, the spacing between pile number 1 and pile number 1 will be 0, obviously. Between pile number 1 and pile number 2 will be 1.5. So that's what we put here, 1.5. Between pile number 1 and pile number 3, it will be 1.5 plus 1.5, that will be 3. And then we need to divide this value, the spacings, by the diameter of the pile. The diameter of the pile is given as 0.3. So we need to divide all this number by 0.3. So we got the spacing to diameter ratio, and then we need to use the chart on your lecture notes to find what's the value of reduction factor R, okay, due to the adjacent piles. And obviously we need to put the type of the pile we are using. So here pile number 1 is of type A, pile number 2 is of type B. So we need to organize that because we need to multiply them by their respective loading, to find what's the influence of the settlements, what's the influence on the settlements of pile number 1 from the adjacent piles. And for the second piles, for the second pile group, which is the one at the center, we need to do the same. So we take one of these two piles, 2 or 5, and we find what are the spacings, what are the spacing to diameter ratio, what's the influence ratio here, and what's the type. And then we need to organize from the first table, we need to get these equations, and from the second table, we need to get the second equations. And after we got that, knowing that the loading on all piles are the same because we are dealing with the flexible raft. So the load on pile group A will be the same as the loading on piles of type B. Knowing that we can arrange these two equations, rho I will be equivalent to the rho naught, which is the settlement of the cap unit. That's multiplied by 2.99 P, which is the loading on the pile itself, okay? And we know that the load carrying capacity of the group alone is 1.56. We have already obtained this from the calculation here. We have already obtained this value, 1.56. So 1.56 meganewton is carried out by the 6 piles. 6 of the piles are of type A and 2 of type B. Knowing that, we can find what's the value of P here. 1.56 equals 6P, because we're going to have here 3 equations. This is equation number 1, this is equation number 2, and this is equation number 3. We have 3 equations with 3 unknown variables, so we can solve this system of equations easily. And then we can find what's the settlements on the pile A and what's the settlement on the pile B. As we can see that the settlement at the center is a bit larger than the settlement on the side. And then we can find what's the settlement of the pile group by finding the average, and that's gonna be 21.62 millimeter. So that's the settlement due to the pile group. And then we need to find what's the settlement due to the raft alone. Due to the raft alone, we can work out what's the load we need to find what's the load carried out by the by the raft itself. So we know that the Polygroup is carrying out 1.56 meganewton. So the raft is required to carry out the remaining of this load, which is 5 minus 1.56, and that's worked out to be 3.44 meganewton. So we need to apply this equation here. We have already been given the equations. This is the settlement due to the raft alone, which is the working load on the raft itself, which is 3.44 multiplied by the B. The B here is 2.5 meter. That's multiplied by 1 minus Boson ratio square. Boson ratio is given as 0.5 here. And the influence factor IS, we can find it here depending on the area. Depending on the area, we can find what's the respective influence factor. So for example, in our case here, we have a rectangle, and this rectangle is with length to the width ratio equivalent to 2, because we have here the length is 5 meter and the width is 2 meters. So if we divide 5 by 2.5 meter, we're going to have the ratio of length to the width as 2, and that will give us the influence ratio as 1.3. So we got the influence ratio as 1.3. We have the modulus of elasticity as Young modulus of the soil as 40 megapascal. So if we apply all these value here, we can obtain what's the value of the rectangular settlement. Obviously, the value of Q, you need to divide the 3.44 by the available area of the, or the cross-sectional area of the raft, as we can see here. You need to divide 3.44 by the cross-sectional area of the pile, but you need to correct these values. You need to put here 2.5 multiplied by 5, and you need to correct this one as 2.5 meter. Okay, and once you have done that, you will get a settlement due to the raft itself. And then if you sum the two values together, the settlement due to the Polygroup and the settlement due to the raft, that will be the total settlement due to the pile raft systems. And that's work out to be 38.4 millimeter. That's the settlement due to the Polygroup itself. And next week, we're gonna continue in this tutorial, in this revision tutorial, and we're gonna do the last two questions, question 3 and the question 4. Thank you everyone for joining me today. Thank you.